Hey everybody, and welcome back to Calc 3 Online. So today we're going to learn about a very useful thing, and they just call it change of variables, which sounds like something you've done, and that's actually because it is something you've done. And that's like you're used to calling it also U sub, but it turns out that there's a lot more going on in U sub than you really know, actually. And today I'm going to basically show you what's really going on and talk about how to kind of deal with higher dimensional cases of U sub. It's basically like a 2, 3, 4 or higher dimensional U sub, whereas before you're kind of used to just doing like a 1D U sub. So I actually want to start it by doing a 1D U sub, okay? And I'm going to do this problem kind of two ways. And I'm going to do it first just like you would do it in like BC, okay? So on the left over here, I'm just going to do a U sub. If you see this problem, you would be like, okay, I'm going to let U equal x squared. So du is 2x dx, right? And I've got a 6x dx, so that means that 3 du is 6x dx. And so then you would do, okay, integral cosine u, and you pull a 3 out, and then you have du, and so you get 3 sine u, and you'd have to put your u back in, so you'd get 3, and I guess there's a plus c, sine x squared plus c, okay? That is absolutely the way to do that, but I'm going to do something. I'm going to get the same answer, but I'm going to do something very different, okay? It's going to show up later on in this video, and you'll see why this is connected to what I'm talking about. But so instead of u equals x squared, okay, I'm going to do a substitute. You can see I'm doing a substitution here, but I want x to be a function of u. So I'm going to still use this, but I'm going to write it as x as a function of u. So, if u equals x squared, then x would equal square root of u, all right? And so I'm going to do the integral cosine x squared, which is square root of u squared, right? And then this is truly, so this is a determinant, okay? But it's a 1-by-1 determinant, which basically just works out to absolute value. So this is just the 1-by-1 determinant of, which really just gives me the number of the partial of x with respect to u. So this part is 1/2 square root of u, right? And so I'm going to put that in, 1/2 square root of u, right? And then du, right? So du is just du, okay, there's nothing really to do with that. But I do still have this 6x I got to put in, so I'm going to do x is square root of u, right, and then I'll have a du. This is like a u integral, right? So I got some stuff I can simplify here. 2 and 6 can cancel the 3. You've got square root of u on the bottom and the top. And so if I simplify all that, right, I'm going to have 3 cosine, oh, and also I'm going to simplify this, right? Square root of u squared is u. So that's u. And then that should be it, right? Yep. So I get 3 times the integral of cosine u du. And then if I do that out, right, I'm going to get 3 sine u, and u was equal to x squared. So I have plus c, and then I get the same thing, 3 sine x squared plus c. Okay, so you might wonder why I went through all that weird stuff to just get to the same answer. We're so used to doing it this way, but it turns out that the reason this works is really because of this kind of formula. This is really what's going on, but no Calc 1 or 2 teacher would ever really show you this because it's beyond the scope of that course. Turns out that this thing, this little determinant in here, has a very important name, and we're going to talk about that today. It's something called the Jacobian, but this is actually how U sub works, and this is what extends really nicely to higher dimensions. This little trick doesn't. This is just a notational trick that we can do because of this. And so I'm going to come back to this later, and I'll show you how this is really like the one-dimensional version of a change of variables. So first I want to just start by going through what we're really doing and like build up what this thing a Jacobian is and kind of all the nuts and bolts of it. So it really is like it's going to be the extension of U sub that you're used to from BC. So, typically here you do, if you see some sort of problem where the derivative of this this inner function is showing up somewhere, that's when you do U sub. And so we could write that this part right here, okay, could be understood as like this could be partial of x with respect to u, right? And then we got this du still. This little thing is what we call that this thing called a Jacobian. And Jacobians, it's named after a person. You've actually been seeing them, okay? And you just didn't know what they were because I didn't tell you. Turns out that r, which we saw in polar coordinates, is a Jacobian. Also, rho squared sine phi is a Jacobian from spherical coordinates. And really, anytime you do U sub and you get something extra, I'm going to say. So extra meaning like over here, right? We get this 3 that pops up, right? That 3 is a Jacobian. It's linked to the Jacobian, I should say. So anytime in U sub to like make this part work out nice, this substitution here with this other piece, you sometimes have to modify and add in something. That thing that you're adding is the Jacobian. So extra, I don't know, piece, we're just going to say. So all those things are Jacobians, okay? And one of the things that you'll do a lot in kind of upper level applied math settings is you do changes of variables to make problems easier. And whenever you change a variable, you just have to remember these Jacobians. You're going to have to add in these random extra terms. And I'm actually going to show you today where this one comes from. And I think next time I'll show you this one in another video. But it's really just a fancy name for one important piece of what like dA or dV. Oops, I just realized I gave myself 2 spots. I meant to do dA or dV become after the transformation. Like when we do polar, right, we have that r dr d theta. This is a Jacobian. It's going to pop up in this weird determinant thing that I'm going to show you, okay? It's the extra thing that's needed to represent this change of variables correctly. So I think it's good to say a little more about what a change of variables is with a picture here. So, we know that polar is x equals r cos theta and y is r sine theta. And we're used to kind of, this sort of picture probably, and like we can get these definitions just by a triangle problem, right? If you do take cosine of theta there, right, you get this x distance, right, over r, this radius, right? And then all we do to get polar is we multiply by r, and that's how we get like, okay, x equals r cos theta. But really what that does is it takes like rectangular things, right? When we do a polar transformation, we're taking rectangular kind of a grid in space, right? And it could map this to a kind of polar little grid. So when you go to like Desmos or something and you change from polar to rectangular, it takes, rectangular looking lines and all of a sudden turns them into little chunks of these like arc chunks like this, right? That's all change of variables. It's whenever you convert from here to here, and you're going to have to account for how this space changes after the transformation. So I wanted to just, before we get into even where this determinant part pops up and all that stuff, I just wanted to basically show you how change of variables works. So what I'm going to do in this example is I'm going to, we have over here something in like a little square, just a unit square in UV space. And I'm going to show you if you have these transformation equations, x equals u squared minus v squared and y equals 2uv. So this is kind of like over here, right? X equals this, that would convert theta r over here in rectangular to this, okay? So with these transformations, I'm going to show you how you can take the unit square, these transformation equations, and get this weird region, okay? And basically the way to do this is it actually looks a lot like when we did maximums and minimums, like when we did absolute maximums and we had to evaluate on the boundaries. That's basically what we're going to do. So I'm going to take like a boundary, like S1, right? And on S1, the important thing is that V equals 0, right? So then what I'm going to do is I'm just going to look at how V equals 0 affects these two equations. So either then x equals u squared, or y is going to equal, 2 times u, but then times 0, so 0, okay? And so what's happening here, the important thing is that this S1 gets mapped to y equals 0. You always just plot the xy stuff, right? So if I can't, like x equals u squared doesn't help me over here, right? But this definitely does. I know that this is going to go here. And so that's just basically what I'm going to do. I'm going to go around the square. So S2, we know that u is 1, right? So if u is 1, then x equals 1 minus v squared, and y is going to equal 2v, right? So then that means that v equals y over 2, right? Which I can also then go back here, and I can combine these, and I can get x equals 1 minus y squared over 4, right? Because you're going to square it, right? So you get y squared over 2 squared. And 1 minus x equals 1 minus y squared over 4 it's labeled right there. But this, so I don't know, let's see, how do I want to color code this? So this one went down here. Then we're going to say that went to here, okay? And then I'll just keep going around. S3, the important kind of feature is that v equals 1. All right, so here, x would then equal just, u squared minus 1. And y would equal 2u, all right? So then, kind of similarly, u would equal y over 2. And then I'm going to do the same kind of thing. I'm going to plug it in here, and I'm going to get that x would equal y squared over 4 minus 1. Okay, and so that means that this top part is mapping here, right? That's y squared over 4 minus 1. And then last but not least, the left side of that square, we know that u is equal to 0. And then if u is equal to 0, x equals minus v squared. And then the more important one is that y equals 0. And so y equals 0 is giving me that part. Let's just do, I don't know what color, how about blue? So this side would map to here. This should feel very similar to when we did the like absolute max and min stuff with in like chapter 14. But so this is just meant to show you how transformations basically work. We can take any x, y equations you honestly want. I mean, there's These are very special ones because they involve like trig and unit circle and stuff like that. But, these ones take this to this, and we just found out that these two ones take this to this. So what we're going to basically be doing is, before we would do like a u sub and we'd let like u equal something. So what we're actually going to be doing is we might start with that idea in mind, like letting u equal something here. But then what we're actually going to do is we're going to rewrite it as x equals that thing with u. So if u equals x squared, that's what we're used to working with, like over here. What we're going to do is what I did here. We're going to switch that around and say, okay, if u is x squared, then x is square root of u. And the other difference is here you would only have ever used one variable, right? Because it's a 1D problem. But now you're taking something in 2 dimensions, right? And you're mapping to something else in 2 dimensions. So you're going to have these 2 equations that can involve 2 variables, which is another big difference. And if you did it in 3 dimensions, which you absolutely can, you would have 3 equations. You actually have done that. You've done it with spherical already and cylindrical, but we'll get to that. So it's just higher dimensional u sub is what we're doing. So I want to go through, really just argue quickly why that determinant part pops up. So we're taking, some kind of chunk in space, and we're doing a transformation. We're getting a different chunk. This is just like generalization of what we're doing, okay? And the idea is to approximate this new region with tangent vectors, okay? And so you can do, we've seen this before when we did like tangent planes and stuff. Like if you want to be thinking on the infinitesimally small scale here. And so these are just, tangent vectors which basically approximate this little chunk really well. And tangent vectors just basically look like this, right? It's like the partial of, the change in x with respect to the u variable and the change in y with respect to the u variable would give me like how much this is changing, right, with u. And then you can do the other partial with respect to v, and you'll get like the 2 directions, right, by doing that. So these are just tangent vectors. And you could extend them, right? If it's a 3D problem, you can go more. But I'm just trying to keep it in 2D for simplicity here. And you can get, so these are secant vectors, okay? And there's going to be a connection I'm going to show you here in a second. So, basically I'm just saying go from like one corner to the other. And so, we're sort of checking the changes in the 2 different directions, which is why it's like fix u naught and then just check the change in the vertical distance and then check the change in the horizontal distance, right? And that's what this represents. So v naught plus a change in v just means like how much are we, this vector could represent how much vertical change there is, and this could represent how much horizontal change there is. To get these equations for these vectors, okay, you literally can just do, this minus this, or this minus this, right? So we can get these 2 secant vectors just by doing subtraction. So we would have this. All right, so we'd have those 2. I'm just literally taking this part minus this, and then this part minus this, right? And those are secant vectors. They're kind of getting me closer to my tangent vectors, I guess, is the idea. And there's going to be a connection here you'll see in a second. So these will become important, basically right here. So we know that the tangent, the way that like a derivative works, basically, just in general, is you start with a secant vector, which is what I got up here, right? And then you let that change in these distances, whether it's change in u or change in v, you let them go, infinitely small, and then the idea is like you get a better and better and better approximation, and so your secant vector turns into what we call this tangent vector. We know that if I'm doing that change in u, right, but I'm not changing it in v there, right? This is just the partial with respect to u for r, okay? And there's this secant vector that comes out of that, right? The top line of that fraction is the secant vector, and that top line could be rewritten as the r with respect to u, tangent vector, but then just multiplied by delta u, right? If you just got rid of delta u, you just multiplied, both sides of this equation by delta u, then it's saying my secant vector right here on the top equals r of u times change in u, right? So that's another true equation. And I could do the same thing here. I could say this secant vector is like approximated by r of v times the change in v, okay? And so what we want to do is we want to take those approximations for the region, right? And we want to figure out the area of this chunk, right? That's like the thing that we're trying to find. And this goes back to chapter 12, I think, right? To get area of like a chunk in space like that, you just take the magnitude of the cross product, something we've seen before. And so the magnitude of the cross product is basically, it's representing the area or the volume or the hypervolume or something like that of that new region post-transformation. And so this cross product with this magnitude in here, it's going to basically be, here I'm doing it with 2D, okay? So this is truly equal to this weird determinant thing, okay? And it's like determinant of something in there. But then delta U, delta V is what you're kind of used to with like dr, d theta, or dx, dy. But more importantly and more generally, it's dA. So this is truly how we figure out the new area after the transformation. And when we do polar, this part in here is where the extra r comes from. It comes from that weird determinant of those two tangent vectors, ru and rv. So the determinant of the cross product of them. I don't know if I said that quite right, but so you have to do the cross product in 3D, right? Because it's not defined in 2D. So we do this kind of weird trick where we take those tangent vectors, these guys, and we basically pop it in with 2 zeros in the k component. And then if you do that out, this cross product in here becomes partial of x with respect to u, partial of x with respect to v. So basically, you're checking the changes in x with u and v, and then you do the same thing with y, changes in y with respect to u and v. And this thing right here is the Jacobian. That is what the definition of the Jacobian is. A lot of times we write it this way. It's a weird kind of just notational trick to say, check all the partials of x and y with respect to all the u's and v's. Okay, so this is just like a weird way to write that, okay? And it's a little small, but you can extend this to any dimension you want. You could keep doing this out, and it really does extend. And basically the Jacobian for an n-dimensional thing is just the partial of whatever your first transformation function is, so it might be literally r cosine theta. So you take whatever that first function is and you check the partial of that with respect to x1, x2, x3, blah, 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 all the x's. You check your second function with respect to all your different things. Your third function, however many you got, you just check them with respect to all the different variables. So this is getting to be some pretty tricky stuff. So I just want to kind of highlight a few really important things I just said. So the Jacobian is specifically the cross product part. Okay, it's this cross product part. this up here, I took the magnitude of the cross product to represent the area. That's something we did in like chapter 12. So you literally do take magnitude, but it's going to translate into just like absolute value. So the Jacobian is inside there, but this is like absolute value. And that makes sense because it's a dA, it's like an area change. And the area change should be positive, like it is an area, or it's a volume or something like that. And so that's like a very subtle but important thing. And it's just a bummer that these notations look so similar. But here you want to think of those bars as absolute value, magnitude. It's like giving me a length, right, of that transformation. And here you're doing a determinant in there to get the cross product part, and that's why there's bars there. So these are determinant bars. These are absolute value, basically, bars. A little subtle, a little weird. All right. So I want to show you that where this extra r in polar coordinates really comes from. So we're just going to determine the Jacobian for the change of variables from Cartesian to polar coordinates. X is our cos theta and y is our sine theta. One thing, too, is that when it comes to determinants, right, because that's really what we're doing here is we're doing you're doing a cross product, but it reduces down to in 2D, it's always just going to be a 2 by 2 determinant. So you can do the determinant of a 2 by 2, and I think I said this in a previous video, if you go like along any row or any column. And so here I kind of mixed it up on you just to show you that it still will work. Here I defined, sorry, I keep going back and forth. I said check x with respect to u, then v, across, and y across with respect to u, then v. Here I'm doing x with respect to r, and then y with respect to r. So x and y are on the same row versus x and x on the same row. So it'll still work, though. You can, as long as you kind of move it around correctly, the determinant will stay the same. So we're just going to do this 2 by 2 determinant. So we're just literally doing like this minus this, okay? So first we got to get all the partials. Partial of r cos theta is cos theta. Partial of r sine theta with respect to r is sine theta. And then partial of r cos theta with theta is minus r sine theta. And then partial of r sine theta with respect to theta is r cos theta. And then now you can go ahead and do your 2 by 2 determinant. You would get r cos squared theta, and then we go minus a negative, so plus r sine squared theta, and then you take an r out, and you have a cosine squared plus a sine squared, and you get r. So this is it's a very important concept. It represents the scale factor change between polar and rectangular coordinates. So one thing that you'll learn if you take a linear algebra class is determinants are basically this thing in linear algebra that represent how it represents the scale factor change in a transformation. So linear algebra, we're basically doing transformations that go from like a linear space to another linear. This is a non-linear transformation, so you wouldn't study this one in linear algebra, but you learn that like a determinant, what it's really doing is it tells you how much the area sort of changes per unit square. So maybe it doubles, and then the determinant would be 2. Or maybe it gets smaller in the transformation, and then the determinant could be like a half or a third or something like that. So r, that variable, represents how much this unit kind of patch area it changes post-transformation. Very important little thing, but that's really why it shows up in polar. It's there because of it is the Jacobian.